This is the AB 91294 review. Calculators are allowed, and it is number 10, the last free response. We've got a differential equation, and we have a particular solution such that the line y equals 2 is tangent to the graph, and we want to find the x-coordinate of the point of tangency and determine whether f has a local max, local min, or neither. Okay, so if y equals 2 is tangent to the graph, that is a horizontal line, so that means the slope dy dx is going to be 0 when y is 2. So if I plug that in, I'll get 0 equals an x plus a 4 over a 3 times a 4. So that's going to equal 0 if x is negative 4. So we have found the x-coordinate of the point of tangency. Now we want to determine whether f has a local max, a local min, or neither. So we know that dy dx at the point negative 4, 2 equals 0. So that means it's a candidate for a max or a min. So to determine whether we get a max or a min, we either need to do the first derivative test or we need to do the second derivative test. The first derivative test is going to be a little tricky because moving to the right or moving to the left when we're in the plane means we can't just change the x's, we also have to change the y's. It can be done, but it's far more complex. So what I would suggest instead is that you do the second derivative test. So let's figure out what that second derivative is going to be, because that might actually make the job easier. If I want to do the second derivative, I will do my quotient rule. So there's low d high minus high d low. Remember, I got to do that implicit differentiation over my low squared. Now dy dx is this expression. So I actually have a 3y squared minus an x plus 4 times a 6y times another x plus 4 over a 3y squared, and that's all over a 9y to the 4th. Now I could, if I wanted, continue to simplify that, but I also can just plug in my point because I know that this is 0 at that point. So this entire thing turns into 0. And I really just have a 3y squared over a 9y to the 4th, which is a 1 over a 3 times the y squared. I end up with a 1/12, which is a positive number. So if we think about what just happened, I have a horizontal tangent and a concavity that is positive. So I can write that y has a local min at negative 4, 2 because dy dx at that point equals 0 and the second derivative at that point was positive. Okay, part B. Let y equal g of x be the particular solution that has the initial condition g of 2 equals negative 2, and I want to find that g of x. So to do that, I'm going to separate my variables, and remember we only need to pull apart or pull over the absolute max, or the min, excuse me. I want to pull over as little as possible. So here, if we go back up here, I moved the y squared to the y side, and everything else I left on the right. So I had a 1/3 times that x plus 4. So now if I do the antiderivative, I'll have a y cubed over 3. I'll move through the constant, get an x squared over 2 plus a 4x, and then I have a plus a c. Now I've got the initial condition. I can plug it in now or I can plug it in later. So looks like I'm dealing with 2's and negative 2's. That doesn't really make it any nicer, so I'm going to isolate first. I'll get a y cubed multiplied by a 3. That will get rid of this. So I'll have an x squared over a 2 plus a 4x plus a random constant times a 3 is just another random constant. So now when I take the cube root, notice I don't have to do plus or minus because it's a cube, it's an odd root. And I'm ready to now plug in my point. So the point comes out as a negative 2 when I plug in a positive 2. So I'll get a negative 2 when I plug in a positive 2. So a 2 squared over 2 is a 2, plus a 4 times 2 is an 8, plus a c sub 2. So I get a negative 2 equals a cube root of a 10 plus c sub 2. So to solve for c, I can either think about what it is that gives me a negative 2 as a cube root. I need the inside to be a negative 8, which would make c sub 2 be a negative 18. Or I can cube both sides and then subtract 10. So I've got my c sub 2. I go back to the expression that I had when I plugged in my point, and I replace my c. And I'm done.